Okay. So in the previous lecture, we just introduced the idea of Bode plots. Okay. So we said it's a very simple graph composed of only straight lines, and but it's a very good approximation to a real frequency response graph. So that's what we said. We said we want to know the frequency response because that's one of the fundamental or a very important characteristic of an amplifier. We need to know what are the range of frequencies over which an amplifier will give me sufficient gain, and a range of frequencies over which an amplifier will reject or offer me very little gain. To know that, I need to know the frequency response. And Bode plots is one very intuitive and a very simple way of drawing that frequency response. So I took some simple examples. We started with a system with a finite DC gain A0 and a single pole 1 plus S by omega P. We drew and saw how the actual response will look like. We took the magnitude response and we took a log of it, 20 log of it, because this is a voltage gain. So we took 20 log of this function and tried to plot it. So Bode plot is a straight line approximation to a nonlinear function. So it's also called as an asymptotic plot. Why is it called as an asymptotic plot? Where does it really match the original plot, the actual plot? I'm sorry, does it match the actual plot, which is a plot of this function? It is close to that, but it only matches it asymptotically. So at 0, at omega equal to 0, it has some match, and then it also matches it near infinity. So it asymptotically matches it, but to a good degree, it represents the real function itself, especially near frequencies omega much greater than omega p or omega much less than omega p. In both these frequencies, the representation is very accurate, very, very close to accurate. At the frequency, for example, a single pole system, what will be the difference between, or what will be the gain of the system? At the pole omega p, let 20 log A0 be the gain at DC. What will be the gain at omega p? 20 log mod of A0 is the gain here. At omega equal to omega p, it will be minus 3 decibels. Minus 3, right? Whatever the gain is at DC, minus 3 decibels. So we discussed this plot. What we did not discuss in the last class is phase response. I'll discuss this in this lecture. For an open loop system, what do you think phase response tells us? What information do you think a phase response of a system conveys for a transfer function that's given like this? Magnitude, we said it tells us that, what is the amplitude change. If you feed a sinusoid with a certain amplitude of a certain frequency, then you can predict from the knowledge of the frequency response graph, the magnitude response graph, what will be the output amplitude. Okay, the phase response tells you the phase difference between the input and the output. When you pass a signal, if you pass a sine wave through the system, amplitude is given by the change in the amplitude in this system is given by the magnitude response. It will be mod of h of omega naught. Let omega naught be the frequency of the sine wave. Vp be its amplitude. Mod of this into Vp will be the amplitude of the sine wave. The phase difference, on the other hand, if I draw, for example, I'll take this sine wave and directly just amplify it without any phase difference. If I directly amplify this, I'll get a response that looks like this. But in reality, there will also be a phase shift. That phase shifted signal will look like this. It will slightly be phase shifted from the input. So this phase shift between the two sine waves, the output and the input sine wave, or the phase difference, is given by the phase response. Now, what use does phase response have? Now, phase response, it's a good indicator of non-linearity of a system. I mean, we haven't spoken about phase distortion and all of that. Generally, it's a topic reserved for filters. But from circuit design point of view, when we are talking about circuit design, phase response becomes very important, especially when we are talking about systems with feedback. So that's why it's very important to understand the phase response of a system. Especially when you have systems with feedback, even though the system is stable in the open loop, maybe when I put it in a feedback, it might become unstable. And that information about instability, you can understand it by looking at the phase response. So that's where phase response comes in very handy. Magnitude response is very important because that's a fundamental characteristic. You need to know what are the range of frequencies for which your amplifier will give you the gain. Phase response becomes more important or critical, especially for systems when they are put in feedback. Okay, so it can tell you how close to instability you are or how stable a system is. So that information you can gather from the phase response as well. And of course, it will coupled with magnitude response, but phase response will give you that information. So in open loop, it may not have a direct application, but when you have a system in feedback, in a closed loop system, phase response will have significance. So that's why we'll try to plot the phase response for this function. The first thing we said is that any function, a Laplace transform, we convert it into a frequency response by substituting s equal to j omega. H of j omega is a complex number. So since it's a complex number, I can treat this a naught by 1 plus s by omega p as a ratio of two complex numbers. So whenever I have two complex numbers, let's assume a e power j phi 1 divided by a2 e power j phi 2. The net function, I can write it as mod of a1 by a2, that's the amplitude of the overall function, multiplied by e power j phi 1 minus phi 2. So the phase gets divided. So you have to take the phase of the numerator complex function and the phase of the denominator complex function and subtract the two. E power j phi 1 minus phi 2 will be the phase. So the phase of the combined function, which is the division of these two functions, is phi 1 minus phi 2. Now let's talk about the numerator function here. What is the phase of the numerator function? A naught here, 0, right? It's just a real number. It's a real number, so therefore there is no complex part. It is 0. So I'll write 0 minus the phase of the denominator polynomial. Sorry, the denominator function, which is 1 plus j omega by omega p. So if you have a complex number of this type, a plus jb, the phase of this complex, if I want to represent it in an organ in a polar form, the phase is given by tan inverse of b by a. Right? So this is a complex number a. This is a here and this is b. It's a complex number. So this is the polar representation of a plus jb. Okay. So this angle here. So this is theta. So this is b. Tan of theta is b by a. So you get the phase here, theta or phi here. I called it phi. Here is tan inverse of b by a. So using that, I can say it is 0 minus 0. This is 0 minus tan inverse of b by a, which will be omega by omega p. So your phase response here is minus of tan inverse of omega by omega p. The phase is a function of omega. What is the value of tan inverse of x when x is 0? When omega is 0, what is its value? 0, right? It is 0 itself. Now when omega is infinity, for a really large frequency, when I substitute omega as infinity, what will be the maximum phase shift of this system? In radians, it will be minus pi by 2 or 90 degrees. In degrees, it is 90. In radians, it is minus pi by 2. So that's it. You know the limiting values. That is, for frequencies much, the function is minus of tan inverse of omega by omega p. For omega much greater than omega p, the phase shift is pi by 2. So that's the limiting value. It will saturate here. And for omega equal to 0, it is 0. And at omega equal to omega p, what will be the phase shift? At omega equal to omega, tan inverse of minus of tan inverse of 1, which is minus 45. Or pi by 4 in radians, minus pi by 4. So this is how the phase response graph will look like. Again, this is just a tan inverse function. Tan inverse x is a nonlinear function. I'll just show a small representation here. So for example, if I ask you to draw tan x, the function tan x will go like this. So let's assume this is 0, tan 0 will be 0. It will go to infinity at pi by 2 and it will go to minus infinity at minus pi by 2. So the tan inverse x function will look like this. If you draw the inverse, tan inverse of x, it will look like this, something like this. You just have to invert it, and this is your tan inverse of x axis, and this is your tan inverse of x. Okay. So x can take minus infinity to plus infinity, and the output will be a unique function. So tan inverse x is a perfectly invertible function, right? So because there is a one-to-one mapping between every value of y and x. So therefore it's a perfectly invertible function. These are very useful properties. Again, even when we are, for example, building some receiver circuits for RF systems, we will exploit these simple properties. So that's why it's useful to understand the mathematics behind every small function that you encounter. You never know where you'll find applications of them. So tan inverse of x is a one-to-one function. So if you know the frequency, for every frequency there will be a unique phase shift. Okay, so that's what this function is telling us. Now we have drawn the phase response for a single pole system. Why is phase response important? I'll take an example and show you that there are two functions with same magnitude response but different phase responses. So let's take this function of this type, h of s equals 1 by 1 minus s by omega p. What is the magnitude response here? If you just substitute 1 by 1 minus j omega by omega p, this is a system. As I said in the first step, we look at a system. If you know the transfer function, you can say if it's stable or not. Is this a stable system? If you see the system, is it a stable system? No, right? The poles are in the right of s plane. The pole is at s equal to omega p. Yes, if omega p is greater than 0, that is the case. It's a right of plane pole, so the system is indeed unstable. Substitute s equal to j omega, you get 1 plus j by 1 minus j omega by omega p. You take the magnitude of this, it will be 1 by root of 1 plus omega by omega p whole square. So if I take 20 log of this, that will be the Bode plot or the Bode plot. This Bode plot will look exactly the same for 1 by 1 minus sb as it was for 1 by 1 plus s by omega p. Both these functions will have same magnitude response. In fact, the function is same. So this is the magnitude response. Until pole, it will be nearly flat. After the pole, the function is going to decay with the rate of minus 20 decibels per decade. Okay. So for example, if you know let's say low frequency response, you roughly know what is the magnitude. Let's say it's 20 log a naught. If I ask you what is the magnitude at 100 omega p, at 100 omega p, so can you tell me what will it be in terms of 20 log a naught? I'm asking you at 100 omega p. Using the straight line graph, what can we say? Minus, so it will be 20 log of mod a naught minus 20 decibels per decade. So if I move omega p to 10 omega p, it would have decreased by 20 decibels. If I move from 10 omega p to another 100 omega p, that's 2 decades. I've traveled 2 decades, so that will be minus 40 decibels. 20 plus 20, 40 decibels. That's it. So this is one very useful thing about Bode plots. You can just look at the frequency roughly, and using the simple relationship of decay, which is minus 20 decibels per decade, you can easily predict what will be the amplitude or the magnitude at any given frequency. And this is very accurate. I mean, it will be very, very close to your actual value, which is you find it from a calculator. Okay, you know the decay rate is minus 20 decibels per decade. Using that, and by the knowledge of the location of the pole, if it's for a single pole system, you can very easily predict the magnitude response at any given frequency. The difference for this system, now I'll come back to the phase response here for this system with the right of plane pole. The phase response will be that it's the ratio of two functions. Again, this will be 0, numerator will be 0, minus tan inverse of minus omega by omega p. So this will be plus tan inverse of omega by omega p. So now if you see here, for this function, the phase response is different. The magnitude response was exactly the same, but the difference comes in the phase response. So that's why we need to know the phase response as well. So now I've shown the phase response here. So now you have a function tan of inverse of omega by omega p. So at omega equal to infinity, what will be the phase shift? Omega equal to infinity will be plus pi by 2 or 90 degrees. Okay, plus pi by 2 in radians or 90 degrees. And at omega equal to omega 2, it will be plus pi by 4. And at 0, it will be 0. Okay, so that's what we can predict from this. So this is the phase response of a system with a right of plane pole. The next function is a system with left of plane 0. I'm going to plot for a system with a left of plane 0, 1 plus s by omega z, and a right of plane 0, which is 1 minus s by omega z. Okay, the magnitude response is same for both. Magnitude response will be root of 1 plus omega by omega z the whole square. This is your magnitude response. Take 20 log of this, and we'll be showing the plot here. So this is an asymptotic plot. You'll show them as straight lines. Start from 0, it will be a constant line. After you encounter the 0, the graph will increase at the rate of plus 20 decibels per decade. It will increase with the slope of plus 20 decibels per decade, and that's same for both the functions. The magnitude response is exactly the same for both the functions. The next one is the phase response. So phase response, first I'll plot it for left of plane 0. Left of plane 0 is 1 plus s by omega z. So the phase response, what will be the phase response for this function? In terms of a tan function or inverse tangent function? 1 plus s by omega z, that is 1 plus j omega by omega z. It will be tan inverse of omega by omega z plus tan inverse of omega by omega z. So you can plot it again. We just plotted it for a right of plane pole. It will look very similar. Start from 0, it will go to a maximum value of plus pi by 2, and it will reach pi by 4 at omega z. So one thing to understand here is that I'll come back to the phase response again. If you look at the phase response of a single pole system, what is the maximum phase shift it can cause? What is the maximum phase shift that the system can cause? Pi by 2, right? So a single pole, the maximum phase shift that a single pole can cause or can introduce to a signal is pi by 2 or minus 90 degrees. It's important, it's minus pi by 2. Okay? So what it means is, for example, if I feed a sine wave of like this, if I feed a sine wave A cos omega naught t, let's forget about the amplitude. Amplitude, I'm calling it omega naught here. Omega naught is much greater than omega p. Omega naught is really much greater than omega p. Using this condition, if I use this condition omega naught much greater than omega p, generally that will be a decade away. If you move a decade away from the pole, we will assume the phase has reached more or less 90 degrees. Okay, the phase has reached more or less 90 degrees. So that's why we will use this relationship roughly 45 degrees per decade. The decay in phase is roughly 45 degrees per decade. Okay, so that's a result we generally tend to use. Again, this is an approximate result, works pretty well. Now, for frequencies omega much greater than omega p, we said the phase shift is pi by 2. So let's assume I'm feeding a signal of this type, A naught cos omega naught t. Tell me, forget about the amplitude, what will be the sine wave? What will the output, what do you think will be the output I get? Let's assume A naught dash is the amplitude. I'm giving you A naught dash as the amplitude. So it will be A naught dash into sine of omega naught t. It will be plus sign, right? Plus, yeah. It will be A naught dash into sine of omega naught t. So what you will get here is that A naught cos omega naught t is your input. The amplitude is going to be modified based on the magnitude response. Okay. So I can write it as A naught upon root of 1 plus omega naught by omega p the whole square. That's your magnitude response. Amplitude will be changed by this. The phase will be cos of omega naught t minus pi by 2. This will be the function. So this cos of minus pi by 2 will be sine of omega naught t. Okay, so this is what we'll get. If you feed a cosine signal, you're going to get a sinusoidal signal. You'll get a sine signal if I feed cosine. Similarly, if you feed a sine, you'll get a cosine. So the signals will be 90 degrees out of phase. So that's the information we gather from the phase response and the magnitude response. Magnitude response will just tell you what is the magnitude change. The phase change information, you can gather that from the phase response. Okay, so now I'll go back to the 0 response. So we'll come back to this 1 plus s by omega z. That's your transfer function of a 0. The phase response is plus tan inverse of omega by omega z. So you will get a function that looks like this. Maximum phase shift is plus pi by 2. It starts at 0 at omega equal to 0, and you will get plus pi by 4 at omega equal to omega z. Okay, so this is other definition. We will now look at a system like this, 1 minus s by omega z. What do you think will be the phase shift of this system? 1 minus s by omega z. It will be the negative of this phase. It will be same as the phase response of a single pole system. It will start at 0, go to pi by 4, and then pi by 2 towards the end. That's it. Max is minus pi by 2. So if you see a right of plane 0 introduces a negative phase shift. Okay, so generally when you add zeros in the system, we said zeros don't determine stability of a system. That's true for open loop systems. If you talk about an open loop system with zeros, you can say that really doesn't affect the stability of a system at all. But the moment you put the system in feedback, zeros will have a significant effect on the stability of a system. Okay, whether they can make the system stable or they can make the system completely unstable as well. And that information we will gather from the phase response. That's where phase response will come in very handy to get an idea about how close to instability we are, at. Okay, so we will discuss that in more detail, probably a little bit in this course and a little bit more in the advanced analog course. And we will see how to design complex feedback systems by looking at the phase and magnitude responses. Right now, we are just talking about open loop magnitude responses and open loop phase responses. Okay, so with this, I've introduced you to an idea about Bode plots. So now you should be able to draw, if I give you some complex transfer function of this type, s by 100 into 1 plus s by 10,000, that is 10 power 4, divided by 1 plus s by 10 cube into 1 plus s by 10 power 6. Now you're supposed to plot magnitude and phase response for this. DC gain is 1. So where do you think the graph will start now? Okay, so what will be the DC gain in decibels for the magnitude response of this graph? Zero decibels, right? DC gain is 0, substitute omega equal to 0, you get 0 decibels. So it's 0 decibels. Now the gain will remain constant. What will it encounter first, a pole or a 0? You can see the value here, this is s by 100. So what will it encounter first? So I will draw 0 a little lower. So it will first encounter a 0, which is at 100 radians per second. The gain will now increase with the slope of 20 decibels per decade. Will it keep on increasing forever, or what will it encounter next? After this 100, what will it encounter next? It will encounter a pole at 1000. So 1000 is a decade away. 100 to 1000, it's a decade away. At 1000 radians per second, it encounters a pole. Now, once it encounters a pole, now what do you think will be the magnitude roughly? Don't worry about the 3 dB correction. What do you think will be the magnitude at this point? So this is 0 here. You have traversed 1 decade. Therefore, this point will be plus 20 decibels. It will be plus 20 dB. Now the gain will remain. See, the 0 is trying to increase the gain. The pole is trying to decrease the gain. So the overall function will remain the same. It will remain constant. What will it encounter next? A 0 or a pole? Now here we have encountered first a 0, then a pole. Now there is 0 at 10 power 4. It's a 0. So 10 power 4 is again decade away. The gain is same. Now it's going to increase. Increase with a slope of plus 20 decibels per decade. What is the next? I mean, what is the next thing that will encounter? Will it be a pole or 0 after this? A pole, right? A pole at 10 power 6. So this is 10 power 4. What will be the amplitude at this point? After that it will saturate because 0 will try to increase it, pole will try to decrease it. What will be the amplitude at this point? 60 decibels. Because you are 20 decibels here and you are increasing at the slope of plus 20 decibels per decade. 10 power 4 to 10 power 6 is 2 decades. So 10 power 4 to 10 power 5 is 1 decade. 10 power 5 to 10 power 6 is 2 decades. So 20 plus 40, this point will be at plus 60 decibels. So this is your magnitude response for the Bode plot. Now we will try to draw the phase response. So before we draw the phase response, keep this point in mind that the maximum phase shift that a 0 can introduce depends whether it's a right of plane or left of plane 0. Since we are speaking about only left of plane zeros now, the maximum phase shift a left of plane 0 can introduce is plus pi by 2 or plus 90 degrees. The maximum phase shift that a left of plane pole can introduce is, I should probably use maximum. I'm talking about sign neutral phase shift. So let's not worry about sign. A single pole can introduce a phase shift of minus pi by 2. That will be the maximum phase shift it can introduce. So now first I'll start the response. Where will the phase response start? What degree, what angle, what will be the phi value it will start at? 0, right? It starts at 0 degrees. Now it first encounters 0. So will the phase, will it be increasing or decreasing? Will it be negative? It will go negative or it will go positive? It will increase, right? Because it's 0 first. It will increase and it will reach 45 degrees at 45 degrees or plus pi by 4 at the 0, which is 100 hertz. And by the time it reaches 1000, which is the first pole, can you tell me what will be the phase shift at that point? See, phase graph, you have to draw it a little bit carefully. You have to keep in mind the pole starts its effect 1 decade before. 1 decade before the pole will start influencing the phase response. Okay, keep that point in mind. The pole will start influencing the phase response almost a decade before itself. So it will go to 45 degrees here. The pole will start contributing to minus 0. I mean, it will start the phase response due to the pole. Pole will try to decrease it to minus 90. 0 will try to increase it from 45 to plus 90. So what do you think will be roughly the response? It will increase little bit, but it will remain more or less constant at 45. Is that fine? At the pole, at omega equal to omega p, it will be 45. Yes, it will be nearly constant. It will be nearly constant at 45 degrees. After 45, what do you think the pole, where will the phase go to? What will be the phase response after 45? Zero's effect has now stopped. You are now at 1000. You look at this 1 decade before 0, we saw the phase start getting affected. 1 decade after it, 0 has no effect. Now what will be the phase shift? It has gone to 45 degrees. Will it increase or decrease? Decrease. It will decrease, right? It will now decrease after a decade. So this will be 100 to 10 power 4. So now this is 10 power 4. It will come back to 0. Look at this. You have encountered a 0 first. I am now standing. Okay. I'm sorry. I'm really sorry here. So yeah. So now let's draw this function. Will it come to 0 at 10 power 4? Because there is already a 0 at 10 power 4. I think that's why some of you were saying it will increase. Yes, it will increase. It will increase. And what will be the value at 10 power 4? What will be the value at 10 power 4? 10 power 4. Is it 90 degrees or is it 45? Think about it this way. The moment you have reached 10 power 4, will there be any effect of the 0 on the pole here? See, you are now 1 decade away from the pole and 2 decades away from the 0. 0 has already created a maximum phase shift of 90 degrees, plus 90. pole has already created, because you have moved 1 decade away, it has created a maximum phase shift of minus 90 degrees. So 90 and 90, pole and 0 effect will cancel out. It will come to 0. Now, what will be the phase shift incurred by 10 power 4? That is your 0. This is a 0. It will be 45 degrees. Okay? So it will be 45 degrees at this point. The effect of the pole, this 0 and this pole is completely gone. Now let me pose you this question. Let's assume there was no 0 at 10 power 4. Let's assume there was no 0 pole or anything at 10 power 4. What do you think would have happened to this phase response? It increased, it came to 45 degrees here. What do you think will be the phase response at 10 power 4? Will it remain constant, or what will it be? What will be the total phase shift at 10 power 4? It will decrease to 0, right? It will decrease to 0. If there was no 0 at 10 power 4, it would have decreased to 0. Look at it. 0 has been trying to increase the phase by plus 90. The pole starts its effect almost, you can look at its effect start to kick off a decade before. You can say it is trying to decrease it to minus 90. So now you are 1 decade away. This is plus pi by 2 and this is minus pi by 2. So it will follow this, remain more or less constant here. And then after this point, this has stopped increasing. It will decrease and come to 0. So is this fine? The graph will come to 0 if there was no 0 at 10 power 4. But now the effect of 0 of 10 power 4 starts 1 decade before. 1 decade before it starts the effect, now it will slowly start increasing the phase. It will take it to plus pi by 4. So therefore I said you can assume more or less the phase response to remain constant here as well. And it will actually reach pi by 4 at this point. Okay, so that's your pi by 4. So now can you tell me what will be the phase response from 10 power 4 to 10 power 5? See, now you are crossing 2 decades. Now what will be 10 power 5? At 10 power 5, what will be the phase shift? Pi by 2, right? It will keep increasing because you have only 1 0. It will keep increasing till 10 power 5 and it will reach pi by 2. What will be the phase shift at 10 power 6? Now the effect of 10 power 6 will start kicking in at 10 power 5. What will be the phase shift at 10 power 6 now? This is pi by 2. See, the pole's effect starts kicking in at this point. It will start decreasing at 10 power 5. And at 10 power 6 it will reach. At 10 power 6 it will reach plus pi by 4. And finally, where will it go to? Will it stay constant at pi by 4 after 10 power 6? If I ask you what is the value of 10 power 7, what will it go to? At 10 power 7, it will come back to 0. That's it. Okay, the total phase shift is 0, right? Because the number of poles is equal to the number of zeros. And all of them are left of plane. So the net phase shift introduced by the zeros will get cancelled out by the net phase shift introduced by the left of plane poles. So finally it will come to 0. So this is how the phase response graph will look like roughly. Okay, so probably I spent a little bit more time. We may not test you on some complex function like this, but this is something you will encounter when you simulate a circuit. Okay, so when you simulate a circuit, you should be able to see some response of this type. If the response is very complicated, we'll rely on simulations. Okay. Now we are done with drawing magnitude and phase responses. And given a magnitude and phase response graph, you should be able to interpret whether you have a pole or a 0. Okay, so we know that from magnitude response, we can easily say, okay, from magnitude response, you can easily say, let me give you a response that looks like this. This is the magnitude response I've given you. Okay, so yeah, so one of you are posing a question in the previous problem. Can you explain why the phase response from 10 power 4 to 10 power 5, why is it increasing? Okay. See, 10 power 4, there is a 0. Okay, there is a 0 at 10 power 4. Now what I said is, look at what is the effect of the two You have a 0 at 100 and you have a pole at 1000. Okay. Now always remember, whenever you are drawing the phase response, whether it's pole or a 0, if let's say you know the location of a 0, the phase response will start kicking in, the effect will start kicking in a decade before. You should look at decade before this. Omega z by 10, and it will last for 1 decade after this. Magnitude response will last forever, but phase response will last only a decade before and a decade after. So let's assume you have a left of plane 0. If you have a left of plane 0, the phase shift, it will introduce a decade before, you can treat it as 0. It will slowly increase. It will reach pi by 4 here and reach pi by 2 at 10 times omega z. You should keep this in mind. Similarly, if I am drawing for a pole, let's say I have a pole omega p, start with a decade before, which is omega p by 10, and a decade after, 10 times omega p. The phase response will start here, reach a value of minus pi by 4 at the, I'm drawing both of them for left of plane and left of plane zeros. Both are for left of plane poles and zeros. It will go to minus pi by 4 and reach a maximum negative value of minus pi by 2. Okay, this is how the phase response will look like. Now keep this in mind and we will draw the phase response for this system. This is a 0 here, this is 0, 1, this is a pole here, and this is a 0 again, 0, 2. We were drawing from the beginning, you said, because we had a 0 at 100, let's assume I'm starting my graph from 10 radians per second. It will increase slowly and reach a maximum value at 1000. 1 decade away, it will reach a value of plus pi by 2. And at omega equal to omega z, it will reach a value of plus pi by 4. Now let's look at the pole omega p1, the phase response due to the pole. The phase response due to the pole, this is 1000 here. It will start 1 decade before, and the phase will start decreasing, and it will reach pi by 4 at that point, which is the pole frequency, minus pi by 4 at the pole frequency, and minus pi by 2 1 decade away, so which will be 10 power 4. When you are at 10 power 4, the 0 has already created a phase shift of plus pi by 2. Now add both the phases. See, it's the addition of two phases, right? Phases will get added up. This is phase due to the pole and this is phase due to the 0. Add the two phases. What will you get? The graph will look something like this. Ideally, this is a nonlinear function. If it's a nonlinear function, the slope here is larger. Okay, the slope here is really large compared to the slope of tan inverse function at pi by 4. It's a nonlinear function with decreasing slope. Ideally, you should see a slight reduction in phase, but you can treat it's more or less constant. In this graph, when I'm drawing it, I treated the phase to be more or less constant, but ideally you will have some nonlinear variation because the slope at this point is not same as the slope at this point. If the slopes were exactly same, it will cancel out and it will remain constant. Okay, but I'm saying it will have some small deviations, but let's ignore the deviation and assume the slope is same. Then it will remain constant. The value will be pi by 4. Now tell me what happens after this. Here it is minus pi by 4 plus pi by 2. So the total phase shift is pi by 4. After this phase shift is remaining constant, but this phase shift is decreasing. So the effect due to this ideally should go to 0. It should have gone to 0. Ideally, if you draw, because this is plus pi by 2 and this is minus pi by 2. Add the 2, you get 0. That's what should have happened here. But our plot has a 0 at 10 power 4. So the moment you say there is a 0 at 10 power 4, you should start worrying about the phase response due to the 0 a decade before. So the 0 will start increasing the phase. It will keep increasing. At 10 power 4, the phase will be pi by 4, and after that it will become pi by 2. So now, at this point, wherein at 10 power 4, I just showed my graph as pi by 4 here. Between 10 power 3 and 10 power 4 also it remains constant because now the pole is trying to decrease the phase. This 0 is trying to increase the phase. So the net effect will remain constant. At this point, the effect of pole is now died down. If pole is no longer in, because you are 1 decade away from the pole. So there is no effect of the pole. Now only 0 is trying to increase the phase, and it will keep increasing for one more decade till 10 power 5. So that's why in this range it is increasing. It is increasing and it will reach a maximum value of pi by 2. After this pole at 10 power 6 will start kicking in, and that will decrease the phase and it will take to 0 eventually. Is that fine? Whenever you're drawing phase response, you have to look at a decade before and a decade after. Okay? Yeah. Okay. So finally, I've given you a transfer function which looks like this. Now from this transfer function, can you tell me what is the location of the pole and 0? I'm giving you the DC gain is, let's assume, 0 decibels. I'm giving you this is 100 and this is say 10 power 4. 10 power 4, 2 decades away, so this is 40 decibels. So can you tell me what is the transfer function? So you have a 0 at 100, so it will be 1 plus s by 100, and pole at 10 power 4, so it will be 1 by s plus s by 10 power 4. What is the DC gain of the system? Can you tell me in non-decibel terms, in absolute terms? DC gain is 1. That's it. Now the question here is, the question you should ask is that I have given you only the magnitude response. From the magnitude response, you know the location of the poles. You can say what is the magnitude of the pole and magnitude of the 0. Magnitude of the 0 and magnitude of the pole. But you can't say if it's a left of plane pole or right of plane pole. That information is not embedded in this graph, right? That ambiguity is still there. It can be 1 plus minus s by 10 power 4. So you can only say location of a 0 or a pole, but you can't say whether it's an LHP or a RHP 0. For that, you have to look at the phase response. Now let me give you the phase response that looks like this. So the maximum phase shift happens to be minus pi. Okay. And at 10 power 4, the total phase shift is minus 3 pi by 4. Okay. Or 135 degrees. So now can you tell me what is the transfer function? The 0 is a right of plane 0. It is 1 minus s by 100 divided by 1 plus s by 10 power 4. Why is the 0 right of plane? Because the phase shift is negative. Even though it is a 0, the phase shift is negative. If the phase shift is negative, then you know it's a right of plane 0. So that's how I need to have the information of both the magnitude response and the phase response to uniquely say what is the corresponding transfer function. Okay, so I need to know both. Only then I will be able to predict the response. I'll stop at this point.